All right, thanks for the invite, and it's a pleasure to speak here. By the way, this Trinitarianism, I can't even pronounce it myself, Trinitarianism. It's sort of a blasphemous term from the Trinitarianism, from the Catholic tradition. In this talk, we're going to be talking about, first of all, I apologize, this is a very mathematical talk, so it's kind of weird to me in a condensed matter seminar. If you have any questions about anything, just feel free to slow me down. It's okay if I don't go through all my slides. I'd much rather you follow the material. So we'll be talking about three separate little players here. On the right-hand side, this is why I'm in the condensed matter physics section right now. We have these building blocks or matrix product states. And it turns out that there's a relationship between this thing and something purely representation theoretic, bimodules for von Neumann algebras, and then something purely in the quantum information theory realm, which are completely positive maps. So these also go by the name quantum channels. I don't know what the background of everybody is here in the room. We're all from different places. But I'll give a mathematical definition of this thing. But you can think of these completely positive maps as some sort of most general transformation you could do in quantum mechanics. Now, there's a nice paper by Sudarshan, more than one paper back in the 90s, I think, arguing that maybe these aren't the most general transformations that you can write down for every single scenario if there is some there's some independence conditions that are implicit in these things. But they're very popular. Okay, so these three things turn out to be connected in a very, very precise mathematical way. So if you're going to take anything away from this talk, you should take away the idea that these are the same thing in some sense. And maybe you can make some connections with whatever. It's a very, very general observation. And these little lines here, they're squiggly. There's some squiggly lines, and there's some straight lines, and there's some dotted lines. And they all have some sort of implicit meaning. I wouldn't worry too much about that. We'll go through and resolve some sort of meaning behind what the squiggliness and the straightness means, but maybe not everything. Okay, so some of these lines already have, people have known for quite some time, since like the 50s and 60s. Right here, this line going from completely positive maps to matrix product states, this is the Krauss decomposition theorem. So every completely positive map can be decomposed in terms of some sum of error maps or some sort of adjoint maps, this sort of thing. This is a purely quantum information theoretic theorem. And then on the other hand here, there's some sort of arrow going up here from completely positive maps to bimodules. And people might not have heard of the Potchkin construction. Maybe you've heard of the Kasparov construction. It's some C-star algebraic thing. But everybody's probably, well, maybe. I think people understand this GNS, Gelfand-Neymark-Siegel construction, where you have a C-star algebraic state, and you can build a representation out of it. That's sort of a special case of this arrow here. So a completely positive map, one type of easy completely positive map is a state on a C-star algebra. And you can build a representation from this thing, and that generalizes to just something for purely any arbitrary CP map and bimodules. Okay, that's this work of Potchkin. Actually, this is in the von Neumann world. All right. So these arrows are kind of known, but our story is going to sort of connect all these things up and put it in more category theoretic terms. Now, I won't be talking much about category theory. I'm going to be, so don't worry about that too. Okay, and these connections are based on my colleagues and I have worked this out over the past like 6 years. Greg Moore is on this paper that we're about to hopefully be done with this year. And then my colleague Roman Gayko, if he would give a talk about this subject, he would give a completely different talk. He's more of a condensed matter physicist than I am, and he would pitch the condensed matter theory side of it. So if you have any questions, I can always point you towards Roman. And he's up for jobs this year. So I couldn't find a picture of him like working really hard. And that's partly my fault, because every time I go out to UCLA, he's out right now. That's why we have this Hollywood sign back there. Every time we go out to UCLA to work with him, I always say, let's go on a hike and just work out on a hike. So that's why the only pictures I have of him are around nature. Okay, but he's a hard worker. Okay, so some motivation behind these connections. Well, it's one of these things where we started out with a motivation and ended up somewhere completely different. Is that there's this work that sort of shows that these RG fixed matrix product states give you two-dimensional topological field theories. And basically, this construction is like a state sum construction. Okay, so I won't really talk about too much about this because sort of our motivations have changed over time. But our original goal was try to understand this from a different perspective. I'm more of the sort of Dan Fried tradition of topological field theories. So I like to think of topological field theories as some objects in a category of Frobenius algebra. So I was trying to think of like maybe there's a different sort of way to see this thing, a bottom-up approach idea. And maybe you can make sense of RG flow, right? What is the RG flow we're talking about with RG fixed? Okay. So another sort of motivation is that you can go purely infinite dimensional with these matrix product states. So perhaps you want to model a state on an infinite spin chain, and the bond dimensions of the matrix product state grow and grow and grow, so you can't model it with a purely finite dimensional thing. So maybe if you're a mathematician like myself, maybe going to infinite dimensional bond spaces is the way to go. And indeed, that's sort of worked out here. I don't put it to any practical use, but it is one sort of motivation. Okay, and now another thing is sort of bond space is actually generalized, and we'll see, I'll argue later on, is that instead of having Hilbert spaces as your bond spaces, you can have von Neumann algebras, for instance, or even bimodules for von Neumann algebras. Okay, and there's some connections here that Roman might be able to discuss. I can point you towards him. This is helpful for thinking about like matrix product states and vertex operator algebras. All right. My sort of I liked about this is from a more mathematical perspective is that this is a fancy repackaging of very old ideas that kind of makes these connections very clear in the language of functors and categories, and it just works out really neatly. And I had another project of myself going on where I'm trying to categorify some measures of entanglement, meaning that instead of having a numerical measure of entanglement, you have something like a vector space or an algebra or something like that. And there is some deep connection between the ideas here and that as well. Okay, so a lot of my talks these days are kind of, I feel like this is basically I draw some diagrams and I just show the connections between them. And so yeah, that's what we're pretty much doing. So we'll start off by talking about the building blocks for these matrix product states. I'll give a name for them in a moment, matrix product factors. And how do I get a completely positive map out of this? So just as a refresher, because I don't know what everybody's background is, the building blocks for our matrix product states are going to be these tensors. Okay, so this is a tensor, and so P, the V here means dual space in the rest of my talk. And the V1 and V0 are going to be called the bond spaces or the virtual spaces, hence V. And the P is the physical Hilbert space. It is the thing where the states we're about to construct live in. Okay, so I can glue these tensors together to make a new tensor. And when I glue them together, I get this composition, and the physical Hilbert spaces tensor with each other. Okay. So there's another perspective on these things, though. Instead of thinking of them as tensors, I think of them as linear maps into spaces of linear maps. So this is just a thing called currying, where I'm just sort of, so I'm taking in a vector in the physical Hilbert space, and I'm producing a linear map from V0 to V2 out of it. Okay. And so some notation in this talk, this L is always going to mean linear maps. And when I just have a single, when I have a single V there, I actually mean endomorphisms. Okay. All right. And so from that perspective, this tensor contraction is just going to look like this thing, where I'm literally multiplying V and T together. Notice that the order is opposite here than the diagram. You can blame Leibniz between the difference of these things. But here, I'm just literally multiplying linear maps together when I take in a pure tensor, and hence the name matrix product, right? So I'm not working with matrices because I'm not choosing bases, but indeed, that's where the terminology comes from. Okay, so how can I build a state out of these things? Well, one stupid thing you can do is literally take the bond spaces to be complex numbers. Okay, I'm a mathematician, so I like to deal with the simple cases that nobody really cares about, but it helps me understand better. And so when I take those bond spaces to be complex numbers, well, my tensor is literally a map from P to C, so it's a dual state. Okay. And so if I really wanted to think of it in terms of a trace, this is secretly what's going on when you're doing, instead of working with C here, you work with general bond spaces. You kind of want to trace over that bond space. And that's another way of thinking of this dual vector. Okay. Now, that's kind of boring when I just have a single physical Hilbert space. What I really want to deal with is a state on a tensor product of these things. And there, I can write this thing out as some sort of tensor contraction of tensors. So here's a nice clean notation for that tensor contraction down here that represents this diagram. All right. And now, there's a general sort of thing where you can start out with a state on a tensor product of physical Hilbert spaces and produce a diagram like this using the singular value decomposition theorem. That's been known for an extremely long time. And yeah, so that actually works in infinite dimensions as well. So yeah, okay. And so what does that mean? Well, if I pair this state with the tensor here, then I get this product of linear maps again. Okay, so hence matrix product state. All right. So how are these matrix product factors, right? The factors in making up these states related to CP maps. We'll discuss that in a moment. But first, for those of you who don't think about CP maps too often, I'll give a mathematical definition. Okay, so A and B here are algebras. So in particular, they're going to be one-element algebras. This thing is completely positive is if I tensor with any matrix algebra, this map is positive, meaning it takes positive. So you can think of A and B as the complexification of like observables. And it's going to take positive observables to positive observables. And why do I think of this tensoring by Mn? Well, I have a physical system, and I extend it by some finite dimensional system, right? It's embedded in some finite dimensional thing. I want to take positive things to positive things. Okay, so it's a very natural thing to look at. So that's some sort of purely mathematical definition. Okay, and so how do I produce one of these things out of a matrix product factor? Well, I can just think of I choose a basis for P, that's what these E sub I are, and I just take the adjoint action here and sum these things up, and this thing turns out to be a completely positive map. All right, and this I is just, the size of this I is just this dimension of my physical Hilbert space here. All right, so how are these connected? How are these CP maps connected to the state? Well, it turns out that the inner product of the state with itself, its sort of norm, can be written as a composition of the corresponding CP maps in this form. So there's some strange connection here. And this evaluation at the identity here, there's secretly a trace over here again. This is just a nice, simple example where it's just evaluation and identity. Okay, so there's some connection between these two things. And more generally, I can take arbitrary expectation values by looking at twisted versions of these CP maps. So they're not always CP, but yeah, there's some twisted version of these things. And this is just a very simple picture. There's some old work of Werner in the 90s where this is said in a much cleaner way. But this just shows you the two things are connected. What's interesting, though, is that you only need to understand the phi at the identity operator to understand kind of everything about the state. You don't need to understand all the twisted versions. So that's some sort of random corollary of the connections that we're going to discuss in this talk. All right. So to go in the opposite direction, I can start from a CP map and produce one of these matrix product factors. And this is what this Krauss decomposition theorem is about. It says that any CP map, right, let's say I didn't know this formula down here, but I just knew I had a CP map. Well, I can always write it in this form. And this theorem tells us how to do that. Okay. So I can produce one of these matrix product factors out of this. Usually it's not said in a coordinate invariant way, but you can do this in a coordinate invariant way without choosing bases. Okay. All right. So I just might as well just move to infinite dimensions at this point because I'm not doing any fancy functional analysis in this talk. Basically, everything I said can be done in infinite dimensions if I replace linear operators with bounded operators everywhere. Okay, so the boundedness gives, before everything was just like, it didn't matter that we had Hilbert spaces. They could have just been vector spaces. And when I moved to infinite dimensions, now I'm really using the topology. And so I need to talk about bounded things. Okay. Everything works still. Okay. And so from that perspective, you should think of the matrix product factor, instead of a tensor in this tensor product space, it is literally a linear map from P to this thing. And then I put on this sort of condition here. Yeah, this extra topological condition so that the CP map still makes sense. Right? So that's one way of generalizing these matrix product factors. It might not be the only way, but it is a good way. A good way because these connections appear when you choose this convention. Okay, so yeah, indeed, why do we choose this is so that we can actually produce CP maps out of these things. In particular, these very kind of special CP maps called normal ones. They're the ones you're usually concerned with when you talk about von Neumann algebras. And what's also interesting, though, is that without this condition, it's kind of hard to talk about tensor contraction. And so you can try to say, well, okay, maybe I just have bounded maps from P to BVW, and it doesn't. You can't talk about tensor contraction anymore. Okay, so there's some good reasons why you would choose this condition. All right, and now I like playing around with TIC-Z. Instead of thinking of this is supposed to be a three-dimensional picture, so this lives in a plane up here, and the physical Hilbert space comes in. When you go to infinite dimensions, the physical Hilbert space plays a different role. That's not clear in finite dimensions, because you can glue the physical Hilbert space to the virtual Hilbert spaces in finite dimensions and talk about different types of matrix product states that are two-dimensional. When you go to infinite dimensions and use these and use the conventions I said, the physical Hilbert space plays a very different role than the virtuals, and you cannot glue them together. And so, yeah, so I like to think of these as like the three-dimensional pictures. And what's cool about these three-dimensional pictures, though, is if you ignore this third dimension and just look from the top down, this is the diagram of a one morphism and some two category of matrix product factors that we're about to talk about. Okay, so it has like this dual sort of role of thinking of in terms of tensors and thinking about one morphisms. Okay, so it turns out that, let's give some names to these two maps, K and S. And yeah, so when the kernel of my matrix product factor is 0, well, I can identify I can recover the physical Hilbert space if I just go from K and then S. So I use sorry, I think I flipped K and S accidentally. Oh, no. So this is a Krauss, and then this is this recomposition. Okay, so yeah, I can always, the dimension of the physical Hilbert space is kind of encoded in the CP map, just through looking at the number of Krauss operators you have. That's what this is saying. And so abstractly, if I go here and then here, I can identify the physical Hilbert spaces, just because they have the same dimension. Hilbert spaces with the same dimension are the same, right? There's an abstract isomorphism. But there's something better if you think of this as in terms of functors. There's a canonical isomorphism between these two physical Hilbert spaces. So that we have more than just an abstract isomorphism. There is a canonical map from one to the other one. Okay, so the physical Hilbert space is really just something canonically associated to a CP map. I think this is it's something that I haven't heard ever said before. Okay, and this comes from there's some adjoint equivalence of categories, and this isomorphism comes from the co-unit of some adjoint equivalence, if those words mean anything to you. All right. So where is this what are the categories involved? Well, there's some category of faithful matrix product factors, meaning the kernel is 0, and this sits inside of some bigger category of matrix product factors. So here I'm fixing the virtual Hilbert spaces, and these are 1 categories. All right. So what is this category? Well, it has objects given by these matrix product factors. Now we need to talk about morphisms. So what are our morphisms? Well, I just have, well, I need some map from T to V, okay? And I'm going to say this is just a linear map on the physical Hilbert spaces that satisfies some pullback condition. So, all right. So this is some notion of morphism. We might not know why we have this right now. Now, there's some condition on these morphisms, which is I say this theta, this underlying map, that's what that theta underlying means. It means the underlying map of this morphism, which lives on the physical Hilbert spaces. Notice it goes in the opposite direction. It's because of that pullback condition. I say this thing has norm less than or equal to 1. Now, if you've done any category theory, this is a familiar condition. And the reason behind it is that it gives good isomorphisms. So we want to say that maps that are invertible are like unitary maps on the physical Hilbert spaces, right? And so without this condition, you can have non-unitary isomorphisms because it's not playing around with the topology on the physical Hilbert space. When I put in this condition, then isomorphisms are unitary. Any map, which is called a contraction that satisfies this, that has an inverse, which is also a contraction, has to be an isometry. It's another name for a unitary map. Okay. Now, why don't I just choose the isomorphisms to be unitary maps, right? I could do that. And it's just boring, right? It turns out this Trinitarianism between these three categories is just about groupoids, and it's not very interesting. But if I allow for these more general things, I get non-invertible morphisms between CP maps. We'll talk about what a morphism between CP maps is in just a moment. Okay. So yeah, and when you have an isomorphism, the CP maps are equal. Okay. If you're familiar with matrix product states, you might talk about conjugation on the virtual Hilbert spaces. I'm just going to ignore this real fast. It basically, the idea is that when you do that, you're quotienting out too many things. It's just too much. Instead, it's better to just, because we don't know where this is more of a mathematical thing, I want to see how general we can get. It's better to just forget about those virtual Hilbert space stuff for now. And it turns out it reemerges in terms of endofunctors on some categories. So you can insert this stuff back in if you want, but you learn a lot more if you sort of ignore that conjugation right now. Okay, so we have this sort of correspondence between matrix product factors and CP maps. And if we think of this in terms of one categories, it kind of goes like this. Notice that by the conventions I've chosen, the CP map goes from bounded maps on W to BV, and this goes from V to W. So this kind of reversal happens a lot. So what should the morphisms be in this category? We kind of know what they are here, maps between the physical Hilbert spaces. What are morphisms here, right? CP maps. How do I relate to CP maps? Well, there's a little lemma that you can prove is if you have a morphism between these things, then the difference between the associated CP maps is again CP. That's very non-trivial. It could be just a general linear map. So this is the pointwise difference of the maps. This is again a CP map. And that has, again, to do with the contractive condition that I wrote down. And so what we can say, I can give a general sort of, this is an inequality here. I say that omega dominates. So omega is a CP map and phi is a CP map. If the difference is CP, I say omega dominates phi. But you can reinterpret this as a morphism. Like I can just say basically, this is a category whose morphisms have a unique morphism from omega to phi if omega dominates phi. Okay, and so this little lemma tells us that, well, this map going from here to here is a functor that takes a contractive morphism into a morphism in this sense. Okay, so that's what I mean by morphism of CP maps. All right, so now for something completely different, right? We talked about, yeah. It's a what? Oh, okay. You want to think? Yeah. So, so one way you can define. Yeah, there's a way to define a star involution on matrix product factors. So it's possible to do things in that and talk about dagger categories and that sort of thing. And this is all related. But that's sort of, it's actually easier to sort of deal with. Basically, you remove the contractive condition and you put a dagger structure in, and these two ideas are related. One, you just deal with the purely C-star algebraic stuff, and the other one, you just deal with normal categories. And I'm deciding to go with the normal category stuff. And you can sort of see the C-star algebraic, like the dagger category structure after you understand this. Yeah. So this is the simpler version of that. That's what I was saying. Yeah. 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 Right. Right. Yeah. 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 Yes. Yeah. Right. Yeah. 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 So actually, right. Yeah. So actually, yeah, I was thinking about this. The way you don't talk about this dagger structure here is by first understanding, like you import it from the MPF version. Yeah. Yeah. And actually, it's better even better than that is the bimodule like equivalence is that you import it into CP. Yeah. So. Yes. Yeah. 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 So yeah, at some basic level, this has no intrinsic dagger structure, but you can like make it into something by understanding these equivalences at the normal category like level. Yeah. Yeah. Good question here. Yeah. So yeah. So we'll move on to something involving bimodules now. So that's the completely different stuff. Now again, it's not completely different in the sense that this is a sort of known correspondence. Maybe not at the categorical level exactly. Not everything has been worked out, but yeah, let's just chat about it real fast. So the kind of bimodules we'll be talking about in this talk are von Neumann bimodules. So A and B are von Neumann algebras. And so what are these things? One, there's a bunch of different manifestations of these, and they're all equivalent. But the manifestation that'll be relevant to us is I think of this M as an algebraic bimodule, and then I have an inner product that's valued in the right von Neumann algebra here. Okay, so it's a B-valued inner product. And then this satisfies some technical, like functional analytic conditions. I have the self-duality condition. We'll talk about what that means in just a moment. And then there's some subtle normality condition. And I sort of throw these away, even though like the paper we're writing, these subtle things are like the hardest part from a functional analytic point of view. But it doesn't really, you don't care about the functional analysis, you can ignore this. Okay. So what are some examples? Well, one idea of something that's self-dual is a Hilbert space. And so these are things where the left and right actions are just C. Okay, so these are CC bimodules. And then another thing we could talk about are normal star representations. So these are Hilbert spaces with some left action, and these are AC bimodules. C because I have an inner product valued in C, right? Okay, so what is something that doesn't have an inner product valued in C, something new? Well, I could just look at a von Neumann algebra itself. So it's an AA bimodule, and the inner product is just this simple thing. Now, it turns out if you understand this, there's a general construction where this is basically everything, right? General AA bimodules are going to look, well, AB bimodules actually look like you start with a big von Neumann algebra and then you compress it in some way. And so this is kind of a generic sort of thing. Okay, now the thing that will be relevant to us is this bounded linear maps between V and W. This is naturally a BW-BV bimodule. So again, the reversal here is because of Leibniz. So I act on the right by BW, and then I act on the left by BV. And the inner product is just this X star Y thing here, okay? And this inner product will appear naturally. Okay, so there's this correspondence between the CP maps between A and B, and bimodules, I call them pointed, meaning they have some distinguished point. And so if I have some bimodule with a distinguished point, so this is a point that lives in the bimodule, I can make a CP map out of it just using that inner product. So I go from A to B, and then I act on that point on the left with A, and I take the inner products of the original point. And remember, this is valued in B, so that gives me some map from A to B. Okay? And you can prove that this thing is completely positive. And now, on the opposite direction, it turns out that you can start with a CP map and produce a pointed bimodule. And this is kind of like, remember this GNS construction. I start with if I take the CP map from A to C, I can produce a unitary representation of A. So B would be C in that case, just through what is called the Gelfand-Neymark-Siegel construction. Okay, so there's some generalization of that. And what you do is I take some algebraic tensor product of A and B. You could put an inner product on it, which includes the data of the it comes from the data of the CP map. I mod out by null vectors, and then my distinguished point is just the identity operators on both of these things here. So this is this construction of Hotchkiss. Okay, so you don't need to understand the details. It just exists. It's very cool. Okay. And now it turns out this can be represented in terms of functors. And the morphisms in this category here, again, this contractive condition comes up again, are just intertwiners between bimodules. So, I forgot to mention that they preserve the points, so they map the distinguished points to the distinguished points. Okay. Okay, so there's some correspondence here. Okay. So now, this is the cool thing. This is new. This is, as far as I can tell, this is the new part. Because we have this category that I haven't really seen before. And these two things are like, these two categories are equivalent. So how can I see that? Well, that's the thing you should really take away from this talk is that matrix product states and bimodules are like, the space of matrix product states is like as a von Neumann bimodule. Okay, so if I fix the Hilbert space and I look at matrix product factors out of that fixed Hilbert space, and I fix V and W as well, I look at that space, it turns out this is a bimodule. This is one of these fancy von Neumann bimodules. So what's the algebraic structure? Well, in finite dimensions, I know this is just a space of tensors. And so I have an action on the left by W. And the V dual, because this is a dual space, I have an action on the right by BV. And so I can write that like this. This can think of as a tensor product of bimodules in some way. And it generalizes to infinite dimensions in some nice way. Okay, so you can prove this isomorphism is here. And then what's the inner product? That's the important part. Well, I can just choose a basis for the physical Hilbert space and just write down this sort of little formula here. And it's valued in VV. Okay, it's valued in the right thing. Okay, and this thing converges because of this condition. So it's some nice Cauchy-Schwarz argument. So this space is a bimodule in this von Neumann sense. Okay, so how do I see the categorical equivalence? So here's a little picture I'll draw. This you should think of as like T here is an object in the category of matrix product factors. And I'm fixing the Hilbert space. So you have this category of Hilbert spaces down here. And so I can kind of forget all the information except the Hilbert space. And that gives me a functor down to the Hilbert spaces. And now the fiber of that thing is a space of matrix product factors from V to W valued in P. And this thing is a bimodule. Okay. So this is like a picture of what the category of matrix product factors looks like. And a morphism between these two matrix product factors is the thing that takes me from T to V. Okay, that's my data. And that comes from some little map down here on the base. And now if I wanted to see how this was related, what's the categorical equivalence with bimodules? Well, I can just blur my eyes and kind of forget everything. And notice that, well, if I just took that data, I can take any point from here to here by just pulling back by this underlying map. And so I have a map between this bimodule and this bimodule given by this pullback. Okay. So now I've gotten I have a functor between the two categories of bimodules. Okay. And this sort of thing is an equivalence because, well, there's some old algebraic stuff about if I have a bimodule between matrix algebras, I can write it in terms of matrices, okay? And if I think of this in coordinate-free way, every algebraic bimodule decomposes in terms of linear maps, some direct sums. This works in infinite dimensions too. If I have a BV-BW module, you can prove some nice functional analytic things. But the better way to think of it is that every von Neumann bimodule decomposes as a tensor product like this. Okay. What's cool though is what is this P coming from? It's coming in a canonical way by looking at sort of maps from BV into M. So the physical Hilbert space, if I give you a general bimodule, I can recover a Hilbert space from it in some interesting way without any choices of coordinates or anything. So there's always a Hilbert space involved there. Okay, so why is it a Hilbert space? Well, that comes from like little Schur lemma thing. I can talk about, if I think of this thing, I can sort of think of this as P star Q. P and Q are maps, and these are equivariant maps, by the way. Okay, they commute with the right action. And so if I look at all maps that commute with the right action on BV itself, this thing is a copy of C. This is a Schur lemma thing. And so I get an inner product naturally on this space. Okay, turns out to be a Hilbert space. All right. So what time is this? Is it 20? All right. So far, we actually sort of just fixed the virtual spaces, right? And we talked about one categories. And we didn't talk about like tensor contraction or composition or anything like that, right? This is just one categorical stuff. What if we want to vary this V and W? That's some two categorical thing. And that's where you get these bicategories. Okay. So I'm just going to flash through this real fast. So what's a bicategory consist of? Roughly speaking, there's a lot more data than this. You have some objects, you have some one morphisms, you have some two morphisms, which are kind of like two-dimensional diagrams. And then you have a way to compose these one morphisms, which is called horizontal composition. And then there's another thing called vertical composition, which is a way to compose diagrams like this. Okay, so this matrix product factor category, its objects are going to be Hilbert spaces, because now the objects, instead of being matrix product factors, are the Hilbert spaces. And secretly, these will actually be type 1 von Neumann algebras. So every type 1 von Neumann, factors, right? The center is trivial. These BVs are sort of, you can recover B from it if you know it's a factor. So the one morphisms are going to be a matrix product factors. Everything is upgraded one level, categorical level. And so the two morphisms are going to be our linear contractions, and then we have this horizontal and vertical composition. All right. So yeah, so again, the same thing with this two category of CP maps, right? I upgrade everything one level. The two morphisms are now this inequality, and then I have these compositions here. And then bimodules, if you know anything about the two category bimodules, it's going to basically be the same thing. And then the only difference is now you have a sort of distinguished point involved. So we just have some point preserving maps. All right, so I just flashed through these. You have some two categories involved here. And now the composition, so before so I have horizontal composition here, which is the tensor product of bimodules. And the horizontal composition of CP maps is normal composition. And then for tensor contraction is the composition for matrix product factors. Okay, so everything sort of connects up there. All right. Okay, so here's our diagram, and then we can resolve it to make something more precise in terms of some two categorical correspondence. So I have this nice diagram of two categories, and these arrows like this mean there's a bicategorical equivalence. And then there's some more subtle things that involve junctions here. And so what are these things at the bottom? Well, this has to do with the fact that, well, before we talked about these special matrix product factors that have no kernel, right? Those are the sort of interesting ones that you care about when you're doing something physical. And those correspond to bimodules that have, where the distinguished point kind of generates everything. So these cyclic bimodules. Now, one sort of subtle theorem is that you can talk about composition in these categories. It's very non-trivial. So before, in this category of bimodules up here, you had some sort of like tensor products, right? But when I take a tensor product of cyclic things, I don't get a cyclic thing back. So I need to compress it to be cyclic again. Now, how do I know that operation is going to be associative? That's really hard. It's similar to if I have a pre-sheaf, if I have a sheaf, take a tensor product of another sheaf, I get a pre-sheaf, and then I compress that down to be a sheaf again. How do you know that's associative? Nobody really tells you too much about this, okay? It has to do exactly with this little symbol here, which is called an adjunction. This is a very special type of a junction. So this is a subtle result that I kind of don't make much too fanfare about, but one result is that these categories make sense. You can put compositional structures here and everything kind of works out and is associative. Okay, so yeah, basically it's something that basically like, you know, your eyes will glaze over and you don't care about, but now you know somebody's done it and it works. All right, and so yeah, these categories include up here in some natural way, and then there's kind of a way to compress and go back down. I just discussed that. So if I start with something that's non-cyclic, I can push it down and just think about its cyclic part, and I could always restrict a matrix product factor to its that should be, say, the kernel complement, not just the kernel. Otherwise, it's 0. All right, and now there's some subtle thing, okay, right? We're restricting to the objects where everything is a type 1 von Neumann algebra here, right? You don't get general von Neumann algebras yet. So the fact that, okay, maybe you don't care about general von Neumann algebras, but everything, so all the ingredients, if you're a mathematician, all the ingredients are there. It tells you maybe you should generalize and figure out new things. And if we do, we can replace these BVs, the target of, basically, you can think of the target of the matrix product factor, with general von Neumann algebras. Okay, and so this BVW, in some natural way, the right thing to do, it turns out, is to use invertible bimodules. Okay, and the physical Hilbert space kind of generalizes in some interesting way. It's not just a Hilbert space anymore. It's a special type of bimodule. Now, which actually is like a Hilbert bundle over the center. Now, if you don't care about this stuff, right? If I restrict to just von Neumann algebras with no center, this again is a Hilbert space on this side. Okay, so you can just think of it as a way to generalize that. All right, and this condition sort of generalizes as well. And then, yeah. You don't have any notion of what? Oh, yeah. Right. How do you define the matrix product state or something like that? Yeah. You need to choose a state. You need to, yeah. So there's no, there's one thing I neglected to mention is that there's some intrinsic choice of state when you're talking about a matrix product. It so happens that, you know, in type 1, you have the tracial state, and it's sort of bigger than everything, and so that's the natural thing to choose. But you can choose like general boundary conditions for gluing together the ends of the matrix product factors. And there, the right thing to do is to insert an arbitrary state. So the choice of state is actually turns out to be there even at the others. You're saying there's no normal states. No. Yeah. There's no. Yeah. There's a choice of. You can choose a normal state, but it's not going to be like what you would call it, faithful. Or, no, I'm forgetting the word. Yeah, we can discuss it afterwards. Yeah. No, there's a way. Yeah, there's a way to kind of do it in type. I don't know what matrix product states kind of mean. Yeah. In that sense, yeah. 2-1 is yeah. Okay, so this diagram actually turns out to generalize into some other diagram, and now the equivalences though don't become equivalences anymore. They relax a little bit into these adjunctions, okay. And so and the choice of data, the natural choice of data now is sort of like a web of Morita equivalent algebras instead of So okay, so that's just. It's some reason this just naturally emerges, this Morita equivalence thing. It's just the right thing to do if you want to talk about composition. What's some little lemma out of this is that okay, this is purely mathematical, but if I take any CP endomorphism, it's gonna decompose into some two pieces. Some inner part which looks like this, right? Some Krauss decomposition, and then some outer part which doesn't look like that. And this is canonical, and you can prove that this is canonical through this categorical equivalence. Okay, it's kind of weird. Now this has been known. These inner maps were studied back in like the 80s by I think it was the 80s, but I forget his name. But yeah, the fact that it's canonical, I've never seen that before. And what's even more interesting is that there's a canonical physical Hilbert space or physical module associated with every CP endomorphism. And so it has to, maybe it's something to do about like the mixture of this map between general algebras, right? Even for finite dimensions, right? Okay. And now, but not only that, but like, what about the outer stuff? Well, you can decompose it even further. For every outer automorphism, there's another CP map part. So there's like pieces that you can sort of peel off from a CP map for every outer automorphism. I should be careful about these sums here in infinite dimension. They could be direct integrals, but this is morally true. Okay. And there's some, there's some sort of version of the Krauss decomposition theorem. And these physical Hilbert spaces kind of appear out of general CP maps. So there's some information there. I don't know what it means. Okay. Now another thing is that you can just think of this as like how can I use this to talk about entanglement? Well, if I had you have the singular value decomposition. I start out with a state on the tensor product of Hilbert spaces, and I can think of it as sort of like again, this is no type 1 Neumann algebra standard stuff. Should be familiar with you for infinite dimensions. I can decompose it this way. And you can think of this diagram on the right-hand side now as like a loop of composable morphisms and matrix product vectors. Right? So what does that gain us? Well, this is some like categorical thing now. And there's all fancy sort of technology you can do and to sort of talk about this thing on the right-hand side. And you can kind of prove entanglement structure about the thing on the left-hand side because you know the bond spaces tell you about the entanglement of the state. When this thing is purely factorizable, these bond spaces are just going to be trivial. Okay? And so somehow this morphism is a trivial morphism when this is factorizable, but it's a non-trivial morphism when it's not factorizable. So yeah, there's all sort of buzzwords you can say here, cyclic objects, and there's like cyclic cohomology, and I don't know how to apply it exactly yet, but it's clear that there's going to be some useful application of that. All right. Yeah, okay, so there's a way to talk about higher order tensors, and I'm not going to really discuss this. So if you just want to talk about more than one-dimensional things, you can talk about some sort of speculative way to talk about higher things as well. Okay, so. Yeah.
There is actually time for the Spanish Inquisition.
Spanish Inquisition, what?
I mean, continuing on your Monty Python theme.
Yes, yes.
You had a nice picture of like fibering of category.
Yeah.
So my question is, what is the total space that you got on the construction of that fiber?
The total space of this thing is so this is a picture of like it's Grothendieck fibration in some way, and this is the category of matrix product factors up here. Yeah, it's the one category of matrix product factors between V and W. It's
the fiber is that, but the total space, so the bearing.
The five. The total space is all matrix. It's just that P is variant, the physical Hilbert spaces. So
and what is a morphism?
The total space is what's the name of the category? I'm going the wrong way. Sorry. It should be.
Sorry.
There we go.
So okay, great. So, okay. Maybe I missed. Yeah. So the morphism is just. I just wondered is there a version of like morphism is MPO or?
No. The morphism is it's a map between the physical Hilbert.
I think that's the MPO.
That's the same thing you're saying? Or?
Yes, sorry, I think I misunderstood.
Oh, okay. Let me draw it down here again. So here I have some morphism between the physical Hilbert spaces.
Okay.
Yeah,
You
and
have
that-
the theta.
Yeah, there's some pullback condition here that
Okay.
that says, yeah. And again, yeah, if you want to talk about like conjugation on the virtual spaces, that's kind of like an endofunctor on this category. And
I see.
so you can make smaller, you can quotient by categorical quotient by those things and make some other categories that, yeah, that's more interesting, to, perhaps, yeah.
Nice talk. This is like very powerful.
In
Actually.
general, yeah.
Yeah. So because I'm coming from the angle of TQFTs, and as you probably know, like you can construct 2D TQFTs from matrix product states. So I'm wondering like what type of QFTs, functorial QFTs in general that you can construct out of these.
Yeah,
information events.
I don't think they're, I don't know. I mean, they're not TFTs in general, right?
Yeah.
So you can think of, originally we want to talk about like RG flow on the category of matrix product factors. And that's kind of like the endofunctor that takes an object and composes it with itself. And the fixed points of this thing are going to be like monoid objects in the category of matrix product factors. And those, you can prove that those are related to algebras. And if you want like semi-simple algebras, which are related to Frobenius algebras, then you could put extra conditions, like you have this dagger structure and stuff like that. And, and then, but morally, they're going to be fixed points of some endofunctor. That was one of our original motivations. I don't want to say, we can talk in private about, I don't want to say too much because I've been more concerned about proving the equivalence than actually, that was the original, I mean, we want to get there and say something cool about the things that aren't fixed points and then RG flow, and then maybe like, you know, invariance for the flow, right? And there's some,
like C theorem.
Yeah, there should be like a C theorem, yeah. We have some ideas about what that should be because the image of the matrix product factor, there's some sort of like inclusions of images as you go down, and this is some sort of like RG invariant.
Right.
Yeah.
Monotonicity.
Yeah.
That
And
would be
so
very
yeah,
nice.
this, I mean, one of the powerful things is that like this inequality on CP maps is like, it puts a lot more structure there than, yeah.
Especially because like you kind of promoted everything to bi-categories, and the one thing I'm worried about is this unitarity condition. Like it's just not coherent. You know, like it doesn't transport to bi-categories.
Yeah.
Unless you just talk about top level subfunctions from what you're interested in. But yeah, we can chat.
You are about this dagger structure thing? Like,
Higher type of stuff.
Yeah.
So, but yeah.
Yeah.
This is very nice. Thank you.
Yeah.
I have a naive question. So is it possible that the MPS describes some like 2D safety or not topological?
Yeah, that was speculation that we had is, yeah, because there's all this von Neumann algebra stuff going on, and we're thinking that maybe like RG fixed points are provably CFTs in some sense. So there's this sort of correspondence. Yeah, we had some ideas, and we've been working on it for a while, and I can't say anything conclusive. But yeah, so the, like RG fixed states correspond to, all right, in the most naive sense, I think it's something more general. This is not quite right. Correspond to these idempotent CP maps. And there's some old theorem by Kahns that these idempotent CP maps are the same thing as these AFD von Neumann algebras or injective von Neumann algebras. And there's like, and then you have these injective von Neumann algebras, you have bimodules, and it's like all the ingredients of a CFT from this. I'm familiar. I don't know if you're familiar with the work of Andre Enriquez, where he talks about the data of a CFT in terms of von Neumann algebras and bimodules. And so the data seems to be there to have a CFT, but I'm not sure if this is quite the right picture yet. I think there's something else going on there. Was that your question? Sorry, I heard. Yeah. I think it's right, but I think it's more subtle than that. It's it has to do with this RG flow. Like I think this needs to be. I think this needs to be really fleshed out to see what it is, to get that data to work out. Yeah.
Questions? If not, let's thank Tom again.